coming in this rainy weather. I see some familiar faces, but I also see new ones. So I thought I'm going to give you a bit of an update as well as intro to the organization which is actually responsible for the event today, the Cambridge Center for Mathematical Imaging in Healthcare. Please excuse if I'm coughing at some point or something like that, because I actually still have a bit of a cold that I developed last week, so please excuse this. Okay, so an intro, very briefly. There are 5 math and healthcare centers throughout the UK, and Cambridge is one of them. We are funded by EPSRC, and each of the centers is focusing on different aspects of mathematics and healthcare. The Cambridge one is focused on imaging. So what is it that our mission is, that our philosophy is in the research that we are doing? We are looking at developing mathematical methodologies, mathematical techniques for clinical, multimodal clinical imaging. Really very much looking at synergies between statistics and applied mathematics. So this is really at the core of what we are doing. This was really the motivation for coming up with this center in the first place. In this context, we are looking at all kinds of clinical imaging problems in neuroimaging, cardiovascular imaging, cancer imaging, and all of this is done by collaborations across the board, starting from statisticians and mathematicians to engineers and physicists, all the way to biomedical researchers and clinicians. Very broadly, the research themes, we are looking at various types of imaging data and making sense of this imaging data, quantifying information in this imaging data. That ranges from multimodal and spectral imaging, PET, MRI, spectral CT, to dynamic imaging data, where you have imaging information that is evolving over time, and you're interested in the actual dynamics and capturing the dynamics. We are looking at imaging data that lives on on non-flat geometries, like for instance the cortex of the brain. And in the context of these different types of imaging scenarios, we are focusing on 3 core themes. One theme is image processing, image analysis method development, that ranges from image reconstruction, registration, segmentation, classification, to actual deriving mathematical models from imaging data, mathematical models for physiological processes, and a prominent example here in the center is the cardiovascular system. But we are also interested in really optimizing the acquisition process at the source of where the imaging data is being acquired by developing novel imaging technologies and enhancing existing ones. The research in the center is done under the oversight of this management team here. This consists of John Aston, who is our statistical lead, James Rudd, who is our clinical lead, and myself, I'm an applied mathematician. And then the center is coordinated not by Rachel anymore, for those of you who know Rachel, but by Josh. And Josh, I still don't have a picture of you, but Josh is over there. And the imaging clinic that I will briefly mention at the end is organized by Stephanie Reichelt, who is one of our investigators in the center, and Bogdan Roman. And that's really a very important component of what we're doing in the center, is this imaging clinic. So I'll tell you a bit about that later. The research we are doing in the center is really only possible by reflecting this mission that I said, this collaboration across the board, also in the team of investigators. Again, ranging from mathematicians and statisticians who are really working on the foundational questions of methodology development and theoretical development behind image processing, image analysis methods, to physicists and engineers who are very much helping us to make this practically relevant and working in the real world context, to researchers in the clinic, so clinicians and medical researchers who are really providing the domain expertise and telling us what their actual problems are. The research we are doing is also in collaboration with industrial stakeholders, with important companies in the remit of biomedical imaging, biomedical image processing. Two of these companies, AstraZeneca and Feedback Medical, are chairing, thank you, are organizing and chairing two of the sessions, one this morning and the other one in the afternoon. Thank you very much again for doing this, Yinhai and Mike. And the heart of the center are, of course, the postdocs, are the researchers. And again, those are ranging from applied mathematicians to computer scientists, engineers, and statisticians. And some of the research that these guys are doing, you will see later on in the poster session and in some of the talks that are coming up. Apart from the core center postdocs, we also have a range of postdocs and PhD students who are not directly funded by the center, but whose research is very much linked to the center activities, who are very integrated in those. And here are just a few examples of people who are working in the center. And then the research work we are doing, the strategy of how we go forward, of the projects that we are focusing on, is developed with the help of an internal and external advisory board that again reflects this range from mathematics all the way to the clinic. The internal board is chaired by Richard Prager, and the external advisory board is chaired by Simon Erridge at UCL. We are also linked to other imaging initiatives, both in Cambridge, but also across the UK. Here are just a few examples to mention some of those, maybe more recent ones. We are part of the Integrative Cancer Medicine project that was funded recently by the Mark Foundation, and Cambridge is also a part of HDR UK, of the HDR UK platforms, one of which is in Cambridge, led by John Danesh. So after this very high-level overview of what the center is and what the center wants to do, what the center is doing, let me just run you really like a whistle-stop tour through some of the projects that are happening in the center, some of the research streams that we are interested in. So before you do anything with images, you first have to acquire them. You have to take measurements, and out of these measurements you have to create an image. Very often medical imaging data is not directly spit out by the machine as an image, but there is a process involved. And so there are various challenges in this process, both at the acquisition side but also at the side when you have the measurements and you render an image out of this. And so basically what we are working on are sophisticated mathematical methods that can turn an image that looks like this into an image where you can actually see something. That the same scenario here, that by both adapting the acquisition as well as adapting how, starting with these measurements you're reconstructing, turning an image, a low resolution image like this into a high resolution image like this, with where the bottleneck, in this case in magnetic resonance tomography, is always the acquisition time. And this is very much made possible by the concept, in this case, of compressed sensing. So similar similar ideas can be used when you're looking at reconstructing images from dynamic imaging data. So here we are trying to both, again, optimize the acquisition, meaning that you want to reduce the acquisition time, as well as optimizing still the resolution you want to get out of these imaging data by complementing what you have given in these measurements by motion, by mathematical models of motion. And we have shown recently that such an approach can really speed up both the acquisition time, but also get you very high resolution images out of that. Another research stream is about combining or marrying up statistics with geometry, making statistics aware of geometry, very roughly said. This means, in this particular case, alluding again to this fact that imaging data very often is given in non-flat geometries, like for instance here on the cortex, how to take into account, when you do a statistical analysis on this data, how to take into account the geometry on which the data lives on. This is one example. Another example is geometry in terms of when you have a patient cohort, you have imaging data of different patients, or you have imaging data of one patient but monitored over time, how to extract correlations or differences between patients, or of one patient, how did the patient change over time. The geometry here comes in terms of registration, so in order to compare them you have to register them to one space, and the classical way of afterwards analyzing this data once you have registered is to do this sequentially, to do the statistical analysis, like for instance principal component analysis, unaware of what has happened to this imaging data before you can actually analyze it statistically. And so this is led by John Aston and Graham Trees, where the idea is to do a hybrid analysis of this imaging data, taking into account at the very end in the statistical analysis all the things that have happened to the data before you actually process it, before you analyze it. So how much did it actually take to register one patient to another might tell you something how different or how similar those patients actually are. Developing all these wonderful sophisticated mathematical methods to analyze imaging data, or to actually build images out of measurements, is complicated by a very important bottleneck in all of this, namely that these methods are computationally very heavy, very costly. And so another research stream in the center is how to speed up these computational methods, how to make them actually feasible, how to make them applicable to imaging data, which is usually very large and very high dimensional. And so here are just two examples. One of them is by Richard Samworth, one of our investigators in the center, and Milana Gataric, looking at dimensionality reduction methods for spectral data, for high dimensional data, for instance spectral imaging data. Another one, again, has to do with reconstruction. There are a lot of sophisticated mathematical reconstruction methods out there that are not implemented in the scanners in the clinic. And the reason is that those are just computationally unfeasible. If you take a measurement, let's say for instance a PET measurement, and then you have to wait for days till you get an image out of this is not feasible in the clinic. And so one of the things that we are doing here is to develop bespoke stochastic optimization methods that actually make the application of these state-of-the-art mathematical reconstruction methods to clinical imaging data possible, such that with, again, the same computational time, you're going from a reconstruction with a standard, not accelerated computational method that renders you an image like this to, and the same measurements are being used to an image that actually where you can see something. Okay, so this is the idea here. This is the research stream that it is connected to this topic of deriving mathematical models out of imaging data, so inferring model parameters out of imaging data, of multimodal imaging data in particular. And in this project, James Rudd, who is our clinical lead, John Aston, the statistical lead, and Yuan, who is somewhere over there. Who is over there? Great. They are looking at contrast-enhanced CT as well as FDG PET to analyze the risk of rupture in abdominal aortic aneurysm. And so here the hypothesis is that apart from looking at the diameter of the aortic aneurysm, also the tissue composition as well as the stress are important for assessing this risk. And this is what Yuan is doing based on these two imaging modalities, developing models that can actually render the risk of rupture in these abdominal aortic aneurysms. So this is an image of the stress across this aortic aneurysm. Now, I've talked a lot about image acquisition, reconstruction, a little bit about statistical analysis and how to take into account geometry in this, and now we also heard about developing models from imaging data. Another component is, of course, very often that we don't have a good mathematical model for extracting information from this imaging data, and this is where machine learning can help, which allows us to quantify information in images by deriving very generic models from the data itself, from training them on labeled images that can then turn into automated algorithms that can be applied, for instance, in the context of personalized treatment planning, in the context of abnormality detection, where John and Yu, who was a former PDRA in the center, have looked at variational autoencoders to do this. So all the methodologies that are necessary to do in an automated fashion to analyze large data sets of images are in this research stream, which, as an overarching approach, looks at machine learning methods. Now, this is what kind of has happened in the last 2 years. So the center is being funded for 4 years. We are now more than halfway through. So we have 2 more years roughly to go. And so what are the kind of things that are now popping up that we are now looking into? And here you have some examples. Let me maybe give you one example in a bit more detail, which can really show you also what we have learned in the first 2 years. And this is the following. So here, let me say in all these approaches that we have seen so far, they all worked on one or other component of this whole pipeline. So at some point, imaging data is acquired, it's reconstructed, its features are extracted from those images. Those features are then used to make decisions for diagnosis, for prediction, for treatment. And that then is applied to a patient, ideally. Now, all of the research themes that I've talked about, they work on one or the other component of this overall pipeline. What we really want to do now and really want to use the last 2 years on is to connect all of these components to each other, such that in the end, the decision that you make is still aware of the actual data that has been acquired in the first place. And this overall pipeline in this way is optimized for the end task, which is the decision making. So this is the idea, and this is a collaboration between Evis Sala and I've missed out another colleague of mine, Ozan Öktem from KTH, and I don't know if he's here. Yeah, with whom we are doing this now. And this is a very high-level description, but I'm happy to tell you more about this later. The overall idea is that you have models for each of those components, but there are certain parameters in these models, and you're optimizing all these parameters for the actual final solution, final question that you want to answer with it. Now, just to finish off, first of all, we are very open and very happy to collaborate with people outside of the center. And in particular, we have means to fund such collaborations. And so please have a look at our website. It's called the Partnership Fund. So this can be used for seed funding projects, for you wanting to organize workshops. Maybe you want to visit us in the center for a while, or you have a PhD student or postdoc who wants to come here for a certain period of time, who wants to work with us. So all of this can be made possible through this partnership fund. So please have a look and talk to Josh in particular about this if you're interested in this opportunity. Now, the last thing I would like to say is about the imaging clinic that I mentioned at the very beginning. And so the imaging clinic really arose from our wish to get closer to actual research in the clinic, to actual medical research questions that are popping up in Addenbrooke's or in other departments in the university. And it is about a drop-in session that is happening every fortnight on Wednesdays, alternatingly between here, the Center for Mathematical Sciences, and the Cancer Research UK Institute in the cafe there. Sessions where people who have maybe ideas for collaborations or just questions about, you know, where they somehow hit the wall and don't know where to go, come and talk to us and see if we can help them in some way, or maybe see if we can, you know, work together on some of the problems that you have. So please have a look also also at our website where these next dates are advertised. The next clinic will happen next Wednesday here at the Center for Mathematical Sciences. And then, as I said, alternatingly between CR UK and CMS. So please come and talk to us. There's no guarantee that we can help you, but we can try. And maybe we can also learn something from you, or very certainly we can, because we want to understand what the problems are and what the challenges are that all of you are facing. And so that's it. I would like to thank you all really again for coming, and I'm looking forward to a really interesting day. The first session is going to be chaired by Yinhai Wang from AstraZeneca, and I'm handing the word over to him now.